All right, so today we are starting a new unit, Unit 3. So we're going to start with our notes on probability distribution. So if we look at our notes, a couple definitions we want to be aware of. A random variable is a variable that has a single numerical value determined by chance for each outcome of a procedure. And then the probability distribution is a description that gives the probability for each value of the random variable, often expressed in the format of a graph, table, or formula. So we're going to look at how often an outcome will take place, the probability that a specific outcome will take place. And we'll look at all the different types of probabilities that come from our probability distribution. So some rules about our probability distribution, some requirements. To be considered a probability distribution, all of your probabilities added together in your distribution must equal 1. So when I add them all up, it should equal 1. All individual probabilities need to be between 0 and 1. We talked about this in Unit 2, that probabilities are always between 0 and 1, because 1 is for certain and 0 is not going to happen. So you can't have a negative probability or a probability greater than 1. It's not a distribution if you do. So if we look at these two examples and the two examples on your paper, we'll see, right, if we look at, here is all of our possible outcomes when we're flipping a coin and it landing on tails. So it either lands on tails or it doesn't land on tails. And there's our probabilities. And these add up to equal 1. So we've met our requirement that each of our individual probabilities, when I add them together, equals 1. And then each of our individual probabilities is between 0 and 1. So if we look at the next example on our page, right, first we would want to check, does 0.23 plus 0.69 plus 0.08 equal 1? It does. And then you can see all of your possible outcomes are here if you're talking about a deck of cards, right? Drawing an ace, a 2 through 10, or a jack through king. And each individual probability is between 0 and 1. So what I'm going to have you do is pause this video, and I want you to determine if each of these is a probability distribution, and if not, why not? Which rule does it not follow? All right, so hopefully you looked at these. So the first thing I would look for is, for each individual probability, are any of them negative or greater than 1? No, so that's good. If I add all of these up, I end up with 0.8. So because it does not equal 1, this is not a probability distribution. So then I'm going to go to the next one. Are all individual probabilities between 0 and 1? And the answer is no. If you look here, this probability is greater than 1. So this is also not a probability distribution. So then the last one, if I look, each of my probabilities is between 0 and 1. And then if I add up all of these values, I would end up with a total of 1. So this one is a probability distribution. All right, so first things first, we always want to make sure we're working. If we're going to talk about probability distributions, we want to make sure that we have one. So checking our requirements or our conditions is important. We also, when we were looking at our vocab words, it expressed that a probability distribution could show up as a table or a graph. So this is the table form, but we can also make a graphical form of this as well. So it looks a lot like the histograms that we did in the last unit. Your outcomes will be your x-axis or your horizontal axis, and then the probabilities will be your y-axis. So if we go ahead and turn our notes over, we can discuss making our distribution and then turning it into a graph. So for our first example, it says, make a probability distribution for the number of boys in 3 children. So if I have 3 children, what's the probability of getting 0, 1, 2, or 3 boys? So first you've got to figure out what are all your options and what are our probabilities here. So one of the ways to do that is to make a tree diagram. We talked about that in Unit 1. But if you think about your first child, your possible outcomes is that you have a boy or a girl. Then for your second child, each of these outcomes has two choices, right? If I had a boy, I could have another boy or I could have a girl. If I had a girl, I could have a boy this time or another girl. And then same thing for your third child. Each one of these has two additional options. So if we kind of reorganize this, we can read each limb individually. So we have a boy, boy, boy option, then boy, boy, girl, then boy, girl, boy, then boy, girl, girl. So I did all my options for this first part. So I'll go down to the girl, first child being a girl, girl, boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. So we can see that, right? We have 8 total outcomes here. So what's the probability that there are 0 boys? So out of the 8 outcomes, there's only one option where you have no boys. You have 3 girls. So that would be 1 out of 8, which we could turn into a decimal. If I do 1 divided by 8, I get 0.125. So then the probability that I have 1 boy, this one has 1 boy, and this one has 1 boy, and this one has 1 boy. So I would have 3 out of 8 here, which would give me a 0.375. Then if I look for my 2 boy options, this has 2 boys, this has 2 boys, and this has 2 boys. So it'd be another 3 out of 8, 0.375. And then 1 where it's all boys, all 3 are boys, would be 1 out of 8. And if we add these up, this equals 1, which is good because we talked about our probability distributions should equal 1. So then if I want to make my histogram, I can draw out my histogram. So my outcomes here, right, number of boys, I could have 0, 1, 2, or 3. And then my probability. And remember, when you're making a histogram, what you count by has to be consistent every time. So if I make this 0.1, this 0.2, this has to be 0.3 and 0.4. So then when I graph, I have to have 0.125, 0.375, 0.375, and 0.125. And that would make up my histogram. So I'm going to encourage you to pause this video, try example 2. And once you're done with example 2, I would try example 3. Figure out if you can come up with a way to organize all the possibilities of rolling 2 dice. We kind of talked about it a little bit in unit 2, but see what kind of option you would come up with for rolling 2 dice. So pause the video and give those 2 a try. So at this point, hopefully you've tried number 2. So you flipped a coin 2 times. So if you think about flipping a coin, right, you would have 0, 1, or 2 tails. If I flip the coin the first time, right, I would either get a heads or a tails. And then when I flip the second time, I get a heads or a tails for each of these options. So I have 4 total options here of how this coin flip went. So then how many of them I got 0 tails would just be this first option. So 1 out of 4 or 0.25. Then I got 1 tails would be these 2 here. So it'd be 2 out of 4 or 1/2, which would reduce to 0.5 if I made it a decimal. And then 2 tails would be this last one. So 1 out of 4, right? There's 4 total outcomes. One of them is having 2 tails. So this would also be 0.25. So then when I make my probability histogram, I put number of tails down here. And then I have 0, 1, or 2. And then my probability goes on this side. And I get, let's just count by 0.1 again. So 0.25 would be about there. Then this is 0.5. And then this is 0.25. So there would be my probability histogram for this one. So for the sake of time, I'm going to skip over number 3. Number 3 is a lengthy problem. Again, I encourage you to try to figure out a way that you can organize this, but then ultimately check your answers on Schoology to see how you did. But there are obviously a lot of different outcomes for X. If you think about the lowest sum you can get from 2 dice is 2. The highest sum would be rolling 2 6s, which would give you 12 when you add those together. So then it's just coming up with all the possible options. How many different ways can you get each of these sums when you roll 2 dice? So again, I would try this one on your own and then check your answers on Schoology. But for the sake of time, I'm going to move on. So if we go to our next page, we're going to talk about finding parts to our probability distribution. So in this unit, we're going to talk about 3 different types of distribution. And for each of them, we're going to talk about mean, standard deviation, and then unusual values. So in this case, an unusual value is just a probability that is less than or equal to 0.05. So when we're looking at a table, we're just looking to see if the value is less than 0.05. What that means is it's just the likelihood of that happening, right? The probability of this happening is less than 5%. So we're not going to often get that result because the probability is so low. And so that's why we consider it an unusual result. All right, so now we're going to talk about how we find the mean and the standard deviation. These are our 2 formulas. They look kind of complicated, but really they're not too bad. To find the mean, all I'm going to do is multiply my X values times my probabilities, and then this means sum. So I'm going to add them all together. So I'll do X times P of X and then add them all together. For standard deviation, there's a little more to it. You're going to multiply X squared times P of X and add them all together. That's this part of the formula. But then you're going to subtract it from the mean squared. So we'll try an example and you'll notice that kind of what the process is for finding your mean and your standard deviation. So let's look at this chart here. All right, so if we think about, it wants to know the mean and standard deviation of the number of spots showing on a dice. So if we roll a dice, what is the probability of rolling each of these values? So if you think about, there are 6 options. You have a 1 in 6 chance of rolling any of these numbers. So my probability for all of these would be 1/6. Right, and the probability of rolling each number individually would all be the same. So now, to find my mean, I'm going to multiply my X times my P of X value and then add these values all together. So you can turn it into a decimal. You can keep it as a fraction. It doesn't really matter. Whatever your preference is fine. I feel like typically we're going to see them as decimals. So, but you are welcome to look at it however you want. In this case, if I do 1 times 1/6, that would just give me 1/6. 2 times 1/6 is 2/6. 3 times 1/6 is 3/6. 4 times 1/6 is 4/6. I think you probably get the point. So then, if I add up all of these together, I would be adding just the numerators. So 3, 10, 21. So I'd get 21/6 when I add these all up. And 21 divided by 6 gives me 3.5. So my mean here, 21/6, is 3.5. All I do is multiply X times P of X and add the values together. You don't divide in this case. This is not a normal mean. This is finding the mean of a distribution. So you're not going to divide by anything. You just add up all those values. So that's my mean, 3.5. So then to find my standard deviation, we're going to start by doing X squared times P of X, but that's not going to be the only piece to this. So if I take each of these and I square them. 1 squared is 1, 2 squared is 4, 9, 16, 25, 36. And then again, I'm multiplying my x squareds times p of x. So I get 1/6, 4/6, 9/6. So then I would add all those up. 1 plus 4 plus 9 plus 16 plus 25 plus 36. And I would get 91/6, which is 15.16 repeating. Now, this is not my standard deviation when I add them all up. Remember, to find my standard deviation, I'm going to take that value and then I'm going to subtract it from my mean squared. Right? I'm going to take that value and subtract it from the mean squared. So when I do that on my calculator, I'm taking the square root, and I could just use this value here, minus 3.5 squared. So I get my mean, or I get my standard deviation is 1.71 when I solve. All right, so I encourage you to try the next one, but we'll go over it together. We're doing the same thing. We're finding our mean and our standard deviation. So again, the first thing I would do is multiply x times p of x. So I'm going to multiply these together. So 0 times 0.18 is just 0. 1 times 0.34 is 0.34. 2 times 0.23 is 0.46. 3 times 0.21 is 0.63. And 4 times 0.04 would give me 0.16. So then when I add all of those values up, so I would do 0.34, 0.46, 0.63, 0.16, I get, that's too high. Oh, I forgot a decimal. 0.16. I get 1.59. So when I add it all, I multiply these all together, I add them up, I get 1.59. That is my mean. That is all we have to do to find our mean. So our mean is 1.59. So now to find our standard deviation, I'm going to start by doing x squared times p of x and adding it up. So 0 squared is 0 times 1.8 is still 0. 1 squared is 1 times 0.34 is still 0.34. 2 squared is 4. 4 times 0.23 would give me 0.92. 3 squared is 9. 9 times 0.21 would give me 1.89. And 4 squared is 16. 16 times 0.04 would give me 0.64. So then again, I'm going to add all of these values up. So 0.34 plus 0.9292 plus 1.89, 0.64. So I get 3.79. That is not my final answer though. Remember, to get our standard deviation, I'm going to take the square root of 3.79, that value I found there, minus my mean squared. So I'm going to take the square root of 3.79 minus my mean squared. So my standard deviation would be 1.12. That's my answer. All right, so that's how we find our mean, our standard deviation, and our unusual results. The last part of our probability distribution that we're going to talk about, if you turn your paper over, is what we call expected values. Expected values is exactly the same thing as finding the mean. So if I'm trying to find my expected value, I am simply trying to find the mean value of the outcome. So exactly what we just did. What this is doing is it's finding your long run average. So if we played this game, whatever game or whatever it's telling us to do, if we did it over and over and over and over again, we would, if it was a fair game, we would expect us to break even. The value of our mean would be 0. If it's not, then our mean kind of tells us what we expect to happen every time that we play. So let's look at a couple examples. So it says, suppose you play a game where you get to pick a 3-digit number. You bet $1. If your number is selected, then you win $500 or you gain $499. The only possible outcomes are you win or you lose. So there's nothing in between. So we can figure out what our probability distribution would look like, and then from there determine what our expected value would be. So again, in words, the only possibility that this works out is you win or you lose. When we talk about it in numbers, this means like what's the outcomes that could happen here. So if I win, I'm going to walk away with $499 extra. Remember, you put $1 in, so you don't win $500. You end up taking home $499 extra. That's your profit. If you lose, all you did was lose $1. All right, so there are 900 3-digit numbers if we get rid of all the ones that start with like 0, 0, whatever. So there's 900 numbers to choose from. So what is the possibility they pick your one number? Well, that would be 1 in 900. Right? There's a 1 in 900 chance that they pick your number, which means, right, these two values have to add up to 1. So there are 899 other options here that you lose, right? These two should add up to 1. All right, so then to find my expected value or my mean, I'm going to multiply my x times my p of x and then add them together. So I'm going to multiply 499 times 1 over 900. All right, let's try that again. I'm getting stuck here. 499 times 1 over 900. So I get 0.554. And then if I do -1 times 899 divided by 900, I get -0.998. So then if I add these two values together, if I take this one plus this one, my expected value is -0.44. What that means, right, this is not a fair game. A negative value means we're going to lose more than we win. If we did this game over and over and over and over again, we'd be expected to lose more than we win. Okay, so again, you might want to pause and try example number 2 on your own, but we'll go over it together here. So a life insurance policy pays out $100,000 if a person dies. The policy costs $600 per year. If the probability a given person lives is 0.9995, what is the expected value of the policy? So we're just assuming in the first year of getting this insurance. This wouldn't work. We'd have to do it a little differently depending on how many years we wanted this to play out. But when we talk about what are the event in words, well, what's the two possibilities that how this plays out? Well, we either live or we die. So if we live, financially, in numbers, what happened? Well, we paid $600 that we're not getting back. So we lost $600 from paying for this insurance. If we die, we would get $100,000, but remember, you put $600 in. So you're not going to get out your total. This is not the total of $100,000. It's $100,000 minus the $600 you put in. So if you do 100,000 minus 600, yeah, you would walk away with $99,400. Sorry. So this is the profit that you would be making since you put $600 in. All right, so now let's talk about the probability. Well, it says the probability that you live is 0.9995. Now remember, these have to add to 1. So if I do 1 minus 0.9995, that tells me that the probability of me dying is 0.0005. So now we'll find our expected value by multiplying these together and adding them up. So -600 times 0.9995 would give me negative 599.7. And then 99400 times 0.0005 gives me 49.7. So then when I add these two up, I get negative $550. So again, this is not fair because it's negative. Fair game is 0. So we can expect that in this case that we would lose money on our insurance as we would end up living instead of dying. All right, so that's kind of all of our pieces and parts to our probability distribution. So there is some practice in your workbook for you to do. It might not be page 83 anymore because the pages have been shuffled around, but there is some practice page to do after this in your workbook, and you can check your answers on Schoology and then use the homework as practice as well.